last couple of years I started discussing quite a lot with statisticians, and probably that's the reason I'm here. So today I want to tell you a few things about the kind of research I do. I'm mainly interested in stochastic analysis, stochastic differential equations, and their applications to various problems. So here in this talk I will present the particular application of using continuous time stochastic dynamics to sample from the distribution, and then I will present the method called multi-level Monte Carlo that will actually allow to do it in a very, very efficient way, and then I will tell you a little bit about the possible extensions of this approach. So a little bit about myself, a kind of research I've been doing over the years. So if you want to come and chat with me about various things. So my PhD was mainly about the probabilistic numerical method. So you know there is typically, when you want to work with the problem, you have a choice either to work with a deterministic method. So an example being you have some complicated probability distribution function. You can find typically some partial differential equation that will give you a description of this probability function. Or you can design a stochastic method, a random method that will also allow you to work and analyze this distribution. And there is a famous connection for Feynman-Katz. And then depending on the problem, on the setting, typically you will do a good job if you will juggle between these two ideas and find the optimal solution. The other problems, I spent some years doing my postdoc working in a group of financial mathematics at Oxford. There where I got exposed to using those stochastic methods in finance. And more recently, I started looking into application in statistics. So that's what this talk is going to be about. And at the end, I'll just mention two new things I'm looking at. Is stochastic interacting particle system that differ a little bit from the particle features that some of you probably know well, and also on mean field approximation. So this is a setup where a priori you start with a very large complex system. This system could consist of, let's say, a population or agents in economy that interact. The system is so complicated that there is not much you can tell about this. To understand it, what you can do, you can take a limit of number of agents going to infinity. So this is an approximation, but then you arrive at something that is actually feasible and allows you to do some analysis and understand the problem a little bit better. And once you understand this approximation, then you try to infer back what it tells you about the system that you wanted to work with a priori. So this is a very exciting research area, but I don't have time to talk about this. But if you're interested, feel free to chat with me after this talk. So something that most of you is probably more familiar is SDEs. So we have a problem of sampling from the probability distribution. So here I assume that I have, in fact, the density denoted here by, does that work? Doesn't. Pi. I take the pointer here. And there are many different ways to sample from this distribution, but one of the very efficient is to build a stochastic differential equation, which is an equation of this form. So this is the equation that evolves with a continuous time. It has a deterministic integral here and a stochastic integral here. And then one can show that when times goes to infinity, the stochastic the probability distribution generated by this random variable is the one you're looking for. Okay, so that gives you a vehicle to sample from the probability distribution by solving the stochastic differential equation. So if you can solve this guy, that gives you a method to generate samples from the distribution. Okay, and that's roughly how it works. So you can generate your trajectory and you can average over your trajectory, and ergodic theorem kicks in, and and you have your result. Okay, so this is a principle, and of course there is many different stochastic differential equations or dynamical models that you can build that will allow you to sample from this distribution. So this is by no means a unique representation. Okay, this is in fact one of the most basic representations I want to start with. Okay, so the idea being that if you want to sample, let's say, from the probability distribution that looks like this, what you can do, you can run simulate the path of the SDE that I showed you, and you will see this kind of oscillating behavior. You know that I have a probability mass here at -1 and 1, so the trajectory somehow jumps between those two wells and spends some time there, and that gives you the picture, what is going on, and how the distribution and the path of the solution of the SDE are connected. Okay. Well, classical, why we want to sample from the distribution, so the classical framework, and I will come to that later, is in the context of Bayesian statistics. Often you know your probability distribution function up to normalizing constant. These are quite complicated. You need to find a way to sample from them, and that's why you don't have a direct access. There is no way you can directly just have a very simple algorithm to sample from this, so you need to do something, and SDE is one of ways to do that. Okay, so we have this continuous time SDE. It is convenient to start with a continuous time dynamics, because for that we have mathematical tools that allow to study this object, understand it well, and then once we have a good understanding of this continuous object, we can then think how I can from there build an efficient algorithm. So in order to do that, I need to introduce a discretization of my SDE. The reason being that, you know, you can write an SDE, you can understand a lot about this, but you cannot solve it in most of the cases, or most of the cases of interest when this function will be interesting. So you need some approximation. So one idea, so one algorithm to sample from the distribution would be to take this Euler scheme. So this is, I have a time step h, and here this guy is square root of h, and this is normally distributed random variable. So this is just a perturbation. One way to sample this is, I know that the distribution of my stochastic differential equation when time goes to infinity has the right, the solution has the right distribution. I know from analysis that this type of approximation stays close to my continuous time dynamics, and the error can be quantified in powers of h, typically. So then what I can do, I can set some terminal time, simulate. I cannot obviously simulate it for infinite time horizon. I simulate it up to some time t, and then I have two errors in my sampling, one coming from the fact that I had to stop at some point, and the other because I introduced some approximation to my dynamics. But I can control those two errors, and so this is so-called what I will refer in the stock numerical analysis approach to sampling. Of course, what you can do, and you can eliminate bias in this method by introducing Metropolis-Hastings step. So here I can treat this as a proposal for Metropolis-Hastings, and then I will accept and reject the step, and that will allow me to eliminate the bias from sampling. So typical MCMC, you have you can start with a random walk, which gives you not very informative proposal. This guy typically will give you something better. Okay. So like I said, you have this the second approach I will refer as a computational statistics approach. The first, numerical analysis. The numerical analysis approach potentially gives you this this extra bias that you have to control. Advantage being you don't have to have acceptance rejection step, which can be quite expensive computationally in particularly in big data applications. Okay, so depends on the problem. You need to make a decision. So once we have all of this, we would then typically, once we have a sample, we would like to approximate integrals of this form. So either it's a normalizing constant or whatever quantity you want to have. You want to calculate integrals of some test function g with respect to this density function that you're interested. And then you need to measure an error. So one of the ways of doing this is to consider mean square error. So this is the integral that I'm interested. This will be an approximation coming from discretization of my SDE and sampling it for some period of time, or using MCMC step. Okay. And what you can show then, if I want to control this number, let's say I want this guy to be less than epsilon square. So I'm using epsilon square because this error is squared. Then you need to think, what is the cost? Cost, let's say, measured by a number of random numbers that you need to generate to be able to perform this integration. And it turns out that numerical analysis approach will give you the cost of order epsilon minus 3. So when this comes from, it comes from the fact that you need to approximate your SDE over this t star, which I denoted time period. Computational statistics is an epsilon minus 2, is better, and this is purely the fact that you don't need to control the bias. Okay? Of course, this is asymptotic result. There are constants there and in front of these numbers. Nonetheless, this is a kind of a picture that it's there at the moment. So we've tried to improve this, and the way to improve this is this multi-level Monte Carlo idea that, well, has been developed by Mike Joyce from Oxford, and I was doing a postdoc with him 5-6 years ago. So I spent a few years working on this method, quite a lot, in fact, on various different applications. So I will tell you what that thing is, and the goal of it is that we want to push further this numerical analysis approach, and to hit this epsilon minus 2, or be very close to this epsilon minus 2 that you obtain with the Metropolis Hastings step, and even in some cases to eliminate the bias completely, although we'll be using a biased samples. Okay? So the question is, can I get the same kind of result that you would expect from MCMC without doing acceptance rejection step? So a little bit more to understand this, let's think about the costs and where the costs are coming from. So this is a slight change on the setup just to make the presentation easier. Rather than averaging over the trajectory, I will be simulating many trajectories and just taking an average in space. That also would give me a result. It just makes the analysis a little bit simpler. So I have my SDE. I will be computing approximations to the integral of this form. Again, I can look at this mean square error that I had on the previous slide, and now let's look into this a little bit more carefully. What is happening? So I can decompose this error into two terms. First, statistical error. So this comes from the fact that I'm using some kind of Monte Carlo approach to sample from the distribution, and the second term is this bias that I told you. This bias comes from the fact that this is a expectation under continuous dynamics, and this is expectation under the discretization. Okay, so that's what you can control. So then what happens is why when I told you that we have this epsilon minus 3, so it's it will be clear from here. If I want this error to be of order epsilon squared, then I need to take epsilon minus 2 samples, and if I know that my discretization converges to the continuous dynamics with order h, which you typically have, you just need to pick this to be of order h of order epsilon, right? Because I have epsilon squared and I have epsilon square, and then I multiply. So I need to multiply number of discretization points times number of samples, and then I got epsilon minus 3. Okay, so this is the standard story for the Monte Carlo. So can we do better? To do better, what we do is rather than having only one grid of discretization to the SDE, we will introduce the whole family of different approximations, and we want to build something hierarchical model for the approximation of my continuous dynamics. So what happens here? I have this approximation as before when I've added the subscript L, and that stands for the fact that I will be considering this should be calligraphical, considering discretizations with various levels of resolution. Okay, so I want to approximate my dynamics on some time interval. I want to start with huge time steps that give me very inaccurate approximation, but they are very cheap to simulate because I just need a couple of steps per time interval, and then I want to refine it. I want to then sample more and more accurate approximations with a smaller time steps. This costs me much more, but somehow if I'm only able to take a very few of them, then there might be a gain. So this is the philosophy. That's what we do, is that the observation is that I can write expected value of this approximation where L is the highest level of resolution as a simple telescopic sum in those level of resolutions. So this is a simple identity, and the idea being now that instead of now doing a Monte Carlo approximation on this guy, I will perform L different Monte Carlo approximations here. Now, so then each guy here will be approximated by the Monte Carlo guy of this form. If I would take independent samples on these two levels, there's absolutely no gain in this method. But what I can do, I can couple those two guys. By couple, there's many different ways you can do, but one idea would be to use the same randomness to generate two different discretizations with different level of resolutions, but based on the same underlying, well, in our case, Brownian path. So if that's the case, if I will be using the same randomness here and here, there is a hope that these two guys will be small. The difference between these two guys will be small, okay? Because these are approximations to the SDEs with two consecutive time discretization. So if I will calculate the variance of this guy as a variance of my Monte Carlo estimator, this samples IID, then my variance of this estimator will be proportional to 1 over NL times the variance of the difference. So if this guy is small, then I will need only very few samples for this. And then you can show that the smaller the time step, the smaller the variance here, and therefore the less samples I would need. Okay? So this is the principle, that instead of generating many expensive paths, I will take very few, lots of very cheap paths, and then I will go up while be increasing my approximation when I will reach the point that I will be taking very accurate approximations, but very, very few of them. And by balancing these two guys, you can solve optimization problem that will show you that you will do very well. And what I mean by very well, you have what you have is the outcome of optimization is here. You have a couple of parameters to consider. The weak error, so this is something what I said I was referring as a bias. So this bias will have some rate here, so it depends how accurate you are. The variance, which will scale with a different parameter. So this is just an abstract setup, and depending on the numerical approximation you will use, that will give you different alpha and different beta. And then you have also the cost of simulating, typically for Euler scheme will be 1. And then you can calculate that the overall cost of approximating your integral can be expressed in this way. And particularly interesting are these two cases, that if the variance, so if you manage to couple these two guys really, really well, such that the variance decay quicker than the cost of simulating the path, or at least are at the same level, then overall cost is this epsilon minus 2. So this epsilon minus 2 is expressed as a computational cost, but this corresponds to the way that your variance scale in Monte Carlo. So this will correspond to 1 over square root of n, okay, in the central limit theorem if you translate those results to the more standard setup. So what's amazing about this? You might say, oh, you're just talking about some epsilons here and there. What's the big deal? Well, the big deal is that epsilon minus 2 is exactly the scaling of the variance in the case that you have unbiased estimator, that you sample, you have access to your samples without any bias. There is no cost. So this is the reason why MCMC gives you epsilon minus 2. So what happens here is that we use biased samples, but because we combine them in a clever way, we are able to get exactly the same result as unbiased estimator. And in fact, with one extra small trick, we can eliminate this bias. Okay? So this is a message from this talk. You can use biased approximation, and if you do it in a clever way, you can have result as for the unbiased estimator. We can have a few improvements. So in particular, we can play additional games that we can change estimators on those to different levels, and provided we will not mess up telescopic sum, and then we can exploit it. So this goes to the idea that, as I said, the better coupling you are able to find, the better outcome you have. So this is a whole industry. So we do it in a few different setups. One of them is this ergodic SDEs. So here I will assume, I need to assume that my distribution is log concave, and then I know that I have the contraction property. So if I start with 2 SDs with 2 different initial conditions, the path will contract exponentially fast under this convexity condition. So there's many different ways we can do multi-level. One of them here is that I want to do the multi-level in time, which is a little bit different. So I want to simulate those paths for a long time, and rather than having this expensive, very long paths, I want to first take cheap, short paths and then improve my accuracy by generating a longer paths. So we build this multi-level in the following way, and I will show you the picture. So how we do coupling. If we run 2 paths starting from the same point, and we will terminate them at different point, like here, the difference between these 2 guys will not be small, okay? And therefore the variance will not be small, and therefore I won't be able to benefit from my multi-level structure. However, if we exploit the fact that we in fact were working with stationary distributions, rather than starting those 2 paths at the same point, I will shift my longer path to some earlier point and start it a little bit earlier. So this is my longer path. I started it a little bit earlier than green, and then I started simulating both blue and green using the same Brownian motion. So this is my coupling, and because combining this with this contraction property, I'm able to have those 2 paths to be very, very close, and therefore my multi-level will work very, very well. Okay, so this is what we do, and it works well. So I'm not showing you the full picture, the full story. I just show you this coupling on the level of SDEs. Then we need to do it for the time discretization, and in the paper with Kostas Zegalakis, Mike Giles, and Sebastian Vollmer, in fact we show that this works for pretty much any numerical scheme. It allows you to work with non-Lipschitz assumptions, so you don't need any. You can work with fairly interesting distributions, and we have theorems that guarantee that your error will be within certain bounds, okay? Within this class of log concave densities, although we did numerical tests for double world potentials, and that works pretty well as well, but we don't know how to prove theorems at the moment. We also extended this to the setup of the SGLD. So what happens, I told you that typically a type of distribution in context of Bayesian statistics you want to deal with is of this form, and if your n corresponds to data points, so if n is very, very, very large, then that means that at every step of my dynamics I need to I will have a huge cost because I need to calculate the sum. Okay. So one of the ideas to deal with this goes back to well, really Robbins Monroe, but E.Y. Tay from Oxford a couple of years back, is to rather than having a full posterior of a full size of your data set, you can take a subsample. You take subsample so that this guy is an unbiased estimator to your distribution, and you hope for the best, and it works pretty well. So what we're doing at the moment, we are also building this multi-level approach in the number of subsamples. So you will start with very few subsamples, and you will be refining. The only delicate point here in the whole analysis is that in the setup where number of data points goes to infinity, what you are actually doing, you are sampling from the Dirac measure, because if you have infinite number of data points, then there is no randomness, no uncertainty anymore. Okay, so there are interesting things that are going there. Of course, you need to couple now in the multi-level where you need to couple somehow how this subsampling on these two refinement levels will work, and we propose a few different methods, and this picture here shows the accuracy and the cost for different levels of subsampling. And this is something you need to trust me that what you expect. And the most recent addition to this, what I'm trying to do with some other collaborators, is that there is a general trend to use type of ensemble methods to improve sampling. And what that boils down is that once you generate your sample, you want to use this sample to tune your algorithm at the same time. Okay, so you can repeat this in this setup of Langevin models, but the difficulty is now in the fact that if I use my subsample to tune my algorithm, then we'll make another step. I think about this step of the Langevin equation. Then I introduce dependence in my sample. So my samples are not IID anymore. Okay, and there are quite a few papers that people do not notice this. It creates some problems. I think it's a very interesting and exciting area of research, but one needs to be careful. And so if you're interested, you can come and talk with me. So, so to summarize, I told you a little bit about the various things we do and how we connect this multi-level Monte Carlo with for the problem statistics. And currently the interest, research interest is in using this adaptive ensemble methods and tackle the problem of more challenging distributions, multimodal distributions in particular. So, thank you.